a nice time for the next hour. We have 4 presenters today, including myself, and the plan is that we will. I have to shift this. Well, the plan is that I will say a short welcome here, and the webinar is supposed to last about 1 hour. It's a hot topic today about getting enough biomasses for the biogas production, and especially in this case, we'll focus on the use of straw for biogas production. I'd like all of you, when not talking here, to mute your microphones to have the best quality of the sound. So I hope that everybody will do that. And then at the end of the sessions, we will have a Q&A session where everybody is allowed to come up with questions. Or you can, during the presentation, write your questions in the chat. Then we will try to follow up on that afterwards. As I said, I'll be starting the meeting with this short welcome, and then I'll try to say a short presentation or give a short presentation of some of the pre-treatment methods that have been used here in Denmark in the past. Then Professor Henrik Møller from the University of Aarhus will make a presentation about the research into optimal utilization of straw in biogas production and some of the latest results for the science part. And then we have 2 companies presenting some of their technologies. We have from Straw to Energy from Lars Visgaard Jørgensen, who is a project sales and business developer in Linka Energy. And then we have a presentation of effective use of straw breakage for biogas, directly or indirectly via beddings, from Henrik Bering Christiansen, who is sales manager in Kinetic Biofuels. Louise, could I ask you to record this, or the recording is on? Thank you very much. And then at the end, we will try to have a question and answer session very shortly, and then we'll finalize about 2 o'clock. I hope that's okay, and we'll start with a small presentation from myself, saying something about the pre-treatment of straw for biogas production, which kind of mechanical and biological methods have been made or been used here in Denmark in the past. And as you can see, one of the reasons to try to use the straw is that a profitable biogas production in Denmark is depending on biogas plants being supplied with biomasses with a higher energy content than manure. Normally, manure has a very low dry matter content and an even lower organic part, meaning that the biogas plants on manure alone, that's normally bad business. So energy-rich biomasses for biogas productions, they must be bought and preferably cheap. And in Denmark, there's a very big grain production, and only a minor part of the straw from these grains are normally used, meaning that there's a possibility to collect more of these straw for the biogas production. So it's obvious to try to look for straw and use that for biogas production. If the farmers have no possibilities to sell the straw, they start, a chopper when they harvest, and then the straw is spread on the fields and not collected. Straw is a cumbersome biomass. It contains mainly of cellulose, hemicellulose, and lignin. And on top of that, the surface is covered with a thin layer of wax. And that means that it's quite difficult to have it suspended in water. It tends to float, and that's why pre-treatment of straw is essential to use it for biogas production. Then a wide range of technologies has been tested to find reliable solutions, and that could be pre-treatment, meaning treating the straw before it's put to the primary digester. It could be inline separation of the partly degassed biomasses and then injection of the fiber fraction to the bioreactor again, or it could be post-processing of some of the fiber fractions. Some of the technologies that has been used in Denmark for several years. A long list here with 15 different technologies: hammer mill crusher, chain crusher, extruders, briquettes, pill press, hay busters, disruptors, grinding, silage, chemical pretreatment, ultrasound treatment, mixing in hot digest state, selective residence time, recirculation of the fiber fraction, composting, and in silage. Then I'll show some pictures. Take this first. Hammer mills have been widely used in different design and different fabricates. Then we have had some extruders and briquetting machines, especially the plant where Henrik is has tested a lot of these machineries. More of this will come later on. We have had special transport equipment. We have had a grinder machine crushing and pressing the straw for pellets. We have had also this about the selective residence time, where you separate part of the biomass from the digester and recirculate the fiber fraction back to the biogas plant to have further degassing or decomposing of the fiber fraction, meaning that you separate the residence time for the different part of the manure. This disruptor has been used as well at Henrik's plant, and very big heavy machinery has been used, like the hay buster, very heavy machine with a high capacity, where you treat the straw and then pile it up again when it's been crushed. Inline treatment has been tried, where you take the straw and chop it. After it's entered to the biogas reactor, you can in fact recirculate part of it through pumps with knives and have it cut further down. But all these mechanical devices, they suffer from mechanical wear. It's very hard material, and these two pictures shows, you can see on the left side one of the hammers from a hammer mill, and on the right side after it's been used for a while. So you see the tear of this iron parts is very heavy. And the biogas production in Denmark, it's on large scale compared to most other places. More than 40% of the Danish gas consumption comes from biogas plants. And in fact, the goal is that we have the possibility or the ability to produce 100% of the Danish gas consumption. And that's the end goal for the biogas sector in Denmark. And It's common in Denmark now that plants are large scales. Small scale plant was used years ago, only a few remains. And most of the biogas plants in Denmark by now is big, upgrade their biogas and inject it to the gas grid system. And this is one of the examples of a major biogas plant. This is a Kiblev biogas plant in the southern part of Denmark, and they handle about 1 million tons of biomass a year. After this 4 presentations, I'll send out a link via mail, and I hope that you will take your time to answer this questionnaire. So we'll make a wrap up of the day, what you think about the content. So I'll send you an email afterwards. So thank you very much. This is my short introduction, and now I'll leave the floor to Henrik B. Møller, who is a professor in biogas production at the University of Aarhus, and he will tell about the research that's done in the University of Aarhus on biogas. So the floor is for you, Henrik.
Thank you, Michael, and you can hear me?
Yes.
Yes, and is it in presentation mode? I don't think it is.
Yes.
It is in presentation mode, so you
Yes.
can. Yeah. Okay. So thank you, Michael, for setting the scene and telling about all what has been done in the years until now, and where I've been involved in quite a lot of the things with straw treatment. So a little about the status on using straw in Denmark. When we look at the amount of biomass, I'll just see if my pointer works. You see my pointer? Oh, I don't think you can, but anyway.
Yes, we do.
You see my pointer? Okay, okay, good. So on a weight basis, you can see that straw is hardly visible, less than 1%. So it's not something on a weight basis that means a lot. Where it is cattle manure, it's absolute top biomass on a weight level. But when we go into look at it at dry matter, where we get the gas from, and my own estimation on how much dry matter is in the biomass, we can see that actually straw is starting to count quite a lot, with around 6-7% of the dry matter. This means that today my guess would be that more than 5% of the gas comes from straw. But when we look at other biomasses, we can see that deep litter, which also contains a lot of straw, it has been expanding a lot, the use of deep litter, and today most deep litter in Denmark go into the biogas plant. So it's the most low-hanging fruit in terms of using straw, and already today it almost is as important as cattle manure in terms of dry matter. When we look at the biogas plants treating straw in Denmark, a lot of plants have some amount of straw treatment. Probably around 40 of the 100 plants today treat some amount of straw, but a lot of them treat very low amount of straw, less than 10,000 tons per year. And only a few plants are in the high league of treating straw with up to 40,000 tons. So it's still a rather small amount of straw, even for the biggest plants. And then how much straw do we actually have available? So for the biogas plants, we have around 6 million tons, almost 6 million tons of straw in total, whereas most is from cereal and a little from raised straw. And today we use it mainly for incineration, feed, and litter. But this means that there's still a lot of available straw in Denmark. More than 2 million tons of straw is available for biogas. Probably not all of it would be available in practice, but there will be quite some. Then we also have quite a lot of seedgrass straw in Denmark, around 125,000 hectares of seed straw, where there also is a lot of straw with around 600,000 tons per year. And this is really the straw that is boosting the biogas sector today. That's the seedgrass straw, because it doesn't have always a good alternative use, and it's easy to make silage from it, and is highly demanded by the biogas sector. Then when we look at straw, how much energy do we actually get out from it? That can be calculated by a lot of different ways. So if we know the chemical composition, we can find out from an average straw, we are somewhere between 450 and 600 liters of methane per kilovolatile solid. We can also put it in a bump calorimeter and measure the energy content by incineration. And here we reach about 550 liter methane per kilovolatile solid. So we have a really high potential, but in real life, it is bacteria who's doing the conversion. And when we have done a lot of experiments in batch assays, and here we are in the range between 210 and 300 liter methane kilovolatile solid. So, and also you can see here the big variation in different experiments. So straw is highly variable in how much gas we can get, but in all cases we are only around 60% of the potential. So there's a huge potential to, if we could increase this amount. And Michael very well described all the technologies that have been used until now, and here we can get somewhere up to 12% extra gas from the straw by, for example, briquetting or extruding or hammer milling and so on. But still, in the pretreatment, there is a high potential that is not that cannot be used today. The way the straw in Denmark is used today is variable. We have the very big amount of straw now going via deep litter into the biogas sector, and a lot of biogas plants treat this deep litter. Then we have a low quality straw. This is used to high extent by different actors, and here ensiling and maceration is the main treatments that used, and a few plants have more than 10% straw in the biogas mix. That's around 2 plants in Denmark have more than 10% straw. Then we have the high quality straw, and if it can of course also be used for ensiling and so on, but also it can be used for briquetting and pelletizing and other technologies with dry straw. And there I'll tell a little about the new types of biogas land that we also have some cooperation with some companies to test, where we use 100% straw. Yeah, but it has been a long journey to reach where we are today. So more than 20 years have gone since the first initiative was there, and today it's still, as you saw on the figures, it is still quite limited amount of the potential that we are using. But to reach the ambitious goal to being complete fossil-free and natural gas-free straw is the most important biomass to get into the sector. Then I'll try to highlight a few examples on how to treat straw. We have had a project for several years with where we are looking at baling and ensiling. And the good things about siling is that we can use low quality straw. We can even take the straw directly from the field before it's dry. So it can be in the very busy periods of autumn where the farmers need to seed new crops. It can be a way to get it away from the fields very, very fast. And if the biogas plants accept this rather wet, there can probably also be a discount on the for the biogas sector to buy it in a lower quality. And during the last year, we have done a lot of experiment with this straw silage, where we have used a lot of different additives and so on. We have added the additives directly in the field, where we have sprayed different additives directly on the straw before baling. And it's things like acetic acid and enzymes and so on to reach a higher gas yield. So, this is some of the straw types and so on we have looked at, and some of the additives. And the conclusion is that all these kind of additives that we used a lot of efforts on testing all these additives, they only have a minor impact. So what really means something to increase the yield of straw by silage process is the water content. And if we go up in water content, we can get around up to around 19% extra gas compared to dry straw. So that's actually quite promising, but a little surprising that all these additives actually didn't have a real impact. Also, when the reason why we get this higher yield by ensiling is the pH decrease during the silage process. And as you can see, if we have around 30% water in straw, we can get a proper silage process without any additives. And we don't need to have any easy degradable sugar or anything. It will happen by itself. And as you can see here with the different additives, they don't really have an impact. It is the water content that really matters. And again here you can see wheat straw that has been ensiled for 10 months. It seems there's a positive impact up to 35%, around 35% water. So yeah. Yes, so around 40% water, then we have a very good silage process. Going above 40% water, it doesn't seem to have any impact. Then, as you told you, we also have this new project here with pure straw, where we're also working with temperature. And traditionally, we have mainly worked with thermophilic processes, mesophilic or thermophilic processes. But we also have microorganisms that actually work even faster than thermophilic if we can increase it to end of 60s, like around 70%. We can see here some examples of briquetting and briquetting to lye and ensiling processes, and we can see that we have these gain on maybe 5-8% extra gas. But we have also seen some example now that we can, with this hyperthermophilic, where we go to almost 70 degrees, that we can really boost the gas production. Something happening with straw when we are going to higher temperature. And we have seen example of up to 40% in some cases extra gas. And this is an example of the setup that we are testing now in Foulum together with Biofuel Technology and Aalborg University in an EUDP project. And we have seen some, in periods, we have seen some very promising results with around 400 liters of methane per kilo volatile solid in some periods. So it seems that there's something here that really can boost the amount of gas we can get out of straw. There's not time to really go into detail with this, but it is a process where we have a pre-process at 68 degrees and then a normal thermophilic process, and with some also filtration on the backside and so on, and ideally some lignin oxidation in the future. We have also worked a lot with thermophilic and mesophilic digestion, and also we had an example here where we have been running for a long period from where we have used inoculum from 4 biogas plants, 2 mesophilic and 2 thermophilic, running it for quite a long period. And there was we had a hypothesis that over time the bacterial consortium would be the same, and the RK, which means produce a gas, would be more or less the same over time. But we could see that we could actually get the same gas yield with completely different amount of microbial consortium. But we could also see that the mesophilic, 2 mesophilic, which is the lower in the graph here, never gets to the same amount of degradation as the thermophilic. So there's something indicating that this high temperature, in this case thermophilic, has a huge impact compared to mesophilic degradation. And time is running quite fast. Also, one thing that is the Achilles heel by adding using straw. So we think we have solved a lot of problems. But one problem when we look at sustainability is that we can see now from 2016 to 2025, we have increased the dry matter from around 5.5% in our digesters to 8.5% in average. We have developed this at AU, this ALFA 2 model, which indicate how much ammonia emissions we will have in the field. And this blue one here is digestate. And as you can see, if we go from 5.5% dry matter to 8.5% dry matter, we will go from around 30% ammonia emission to 50% ammonia emissions of the total ammonia we have in the digestate. So it's a tremendous challenge we have here, and it's the yellow one here is cattle manure, and you can see with the same dry matter, but here you can see because of the higher pH combined with the high dry matter, we have a real issue here. And looking at sustainability, we have some challenging here. We have also done a sustainability analysis of different biomasses going into biogas plants, and this is been published scientifically and also in a report from Aalborg University not so long time ago, and there's not time really to go into details with this, and you can read the reports and scientific publication yourself. But the main thing is that we looked at 5 different biomass compositions. We have a quite manure-based system, and we have a very straw-based system, and then we looked at kilo CO2 equivalents per ton, and we have on the positive side, of course, we have the gas to the grid. That's what counts most. But besides that, we also have a reduced methane during storage, especially from manure-based plants. But when we go to the straw-based plants, we have this much higher energy yield per tons of material. So we have a very good sustainability of the straw. And I also did a calculation with next generation straw, where we only use straw, which have a really, really high CO2 impact because of the very high energy density in the straw. And if we take CCS, carbon capture storage, into account, we can really have a high CO2 impact, And especially for straw, where quite a high amount of the carbon is converted to CO2. We have only around 50% methane from straw conversion. We have a very high additional effect of carbon capture storage. Yes, and I'll come to the conclusion now and say that straw plays an extremely important role for the further development of the Danish biogas sector. Today, if we include the deep litter, around 20% of the gas yield already comes from straw and straw-rich products in the Danish biogas sector, and that is going to increase dramatically if we have to reach the national goal. And there's a huge potential to increase the yield from straw, where we only today get around 50 to 60% of the yield. And also these new generation straw plants with monodigestion and very high amount of straw we can achieve a very high greenhouse gas reduction. We have some challenges with the fertilizer products which we need to solve. And then also for straw, it's important that we also is able to include the CCS value because of this very high amount of CO2 we have from the biogas from the straw also. So I will end my presentation by this, and thanks for your attention.
Thank you very much, Henrik. That was a very nice presentation. If any questions, please write them in the chat or save them for the question and answer session at the end of the webinar. Now we'd like to give the floor to Lars Visgaard, who's from the company Linka Energy. So please, Lars.
Thank you, Michael. And thank you for inviting me today to this webinar. It's a pleasure for me to tell a little more about our components and our solutions to treat straw into the biogas digesters.
Oh, you just muted yourself, Lars.
Sorry. We have developed this machine we are calling STB. It's straw to biogas, and we are transforming straw into renewable energy, into gases. And why is it not?
So we can hear you again now.
Yes.
You're muting.
Now it's working again.
Yeah.
First of all, I will talk a little about Linka. We are founded in 1978, and our headquarters is in Lem in Denmark. Worldwide, we have around 5,000 plants. And our first and our main thing was making combustion plants to district heating and to industries, farmers, and so on. And it have been our focus to burn straw, but now our main focus with the straw is to putting it into the biogas sector instead. We are 50 employees today in Lem. This is our straw to biogas line. I don't know if you can see my mouse, my pointer here, then I'll take you through. First of all, our automatically crane are putting the bales here at our pushing table. We need to imagine there is a wall here. So it separates the storage area and the process room in two places. Then the fire gate here is opening, and we're pushing one bale at a time into the process room. Let's make sure that we are not risk fires into the storage area. Then the next step will be our conveyor belt here. The conveyor belt are moving the straw bales to our shredder. Before it's reached the shredder, we are taking all the strings off. The strings are placed in a container beside the string remover. And then it's moved to the shredder. The shredder is just taking the bales apart. It's not cutting the bales into smaller pieces. When it's taken apart, it's ending up here in our double auger. This screw conveyor or double auger are transported directly into a hammer mill here. The first mill is treating the straw before it's transported with vacuum to our main mill. So that means the first mill here are treating it into 25 to 50 millimeter, and our main mill here are treating it to 2.5 millimeter in the length. We are also doing cases where we only have one hammer mill. If their retention time into the digesters is long enough, then it's enough only to treat it down to 25 millimeter, but I will tell you more about that later. In the project phase, we are doing process diagrams and components lists to all of our projects to make sure that everything is aligned with the electricians and in your project phase also. On all of our systems, we are putting a spark ignition and firefighting system from Grecon. It's make sure if there should be a fire or ignition into our systems, it's immediately gonna be stopped with some sensors and a spray nozzles into our auger systems or under the bed or under the mill. This is a approved system from German insurance companies. Now we are coming to the important part. This is the OPEX calculator that we have done, and we have done it in 4 different types of straw. Length 2.5 millimeter, 12 millimeter, 25 millimeter, and briquettes. So as you see, if we need to treat the straw into 2.5 millimeter, the power consumption is pretty much higher than if we are only treating it into 25 millimeter. If we're treating it into 25 millimeter, it's taking 42 kilowatt per tons of treated straw. And the wear parts, oh, my mouse was here. The wear parts is the open part here. It's only to take 0.5 euro cents in wear and tear parts to produce 25 millimeter straw instead of 2.5 millimeter over here, which is taking 0.77 euro cent in wear and tear parts per tons of produced straw. Let's take the next slide, if I can do that here. And then I will talk a little about the gas yield into the straw. Henrik was also talking a little about it before, but the retention time into the digesters is important when we are talking about using straw into the digesters. In our point of view, the best case is to have around 55 to 70 or 75 days into the digesters. Let's make sure that we have enough time to get most of the gas out of the straw before it's leaving. In some of our cases, we are using recirculated straw to mix with recirculated manure to mix with our straw before it's pumped directly into the digesters. In our point of view, straw is it's an important thing to use into the biogas sector. As Henrik also was talking about, there is a lot of energy into the straw, and it's not collected in many countries. We are good in Denmark to collect straw, but in the southern part of Europe, there is a lot of straw available just to make energy. It was a short but good. I think it hold my time. it was all from me.
Thank you very much, Lars. That was a very nice presentation from you as well. And if anybody has questions for Lars, please write them in the chat or write them down and post them afterwards at the Q&A sessions. So now I'd like to give the floor to you, Henrik. Could you share your presentation? It's not in presentation mode yet, but it's there. You have to, yes, this one. Oh, it's on. You have to unmute.
Now it helps. Now I got everything right. Henrik Christiansen is my name. I'm from the company Kinetic Biofuel. I'm going to speak about straw briquettes for biogas, either directly or indirectly via bedding. So let's jump into this right away to keep the time. Why should you use straw? I mean, it's already been told what equipment is needed. We already seen something from Lars from Linka. What are the operating costs? Lars was that helpful in sharing that as well. And then some advantages and who is Kinetic Biofuel. Why should you use straw? I mean, it's obvious for all of us that first generation raw material like maize or corn shouldn't be used for biogas. Straw with a high dry matter is a perfect raw material. And in most places, you know, you are restricted in how much first generation you can use. So the right way is, of course, to go for straw. Is the straw available? Henrik B. Møller mentions there's plenty of straw available. It's correct. You see here in Europe, you see the dark brown places. That's where there are large amounts of available residues. In Germany here, you see the dark red ones. Sorry for this. You see the dark red ones here where there are straw available. In Denmark, you know, we are fighting a little bit for the moment being on prices for straw. There was 2 years of bad harvest, which made the prices go up and hasn't been that helpful for the industry. How is it that straw can't be used? I mean, we already heard there was wax on the outside. Here there's a picture of a straw. You see all of the whole pores cells with air trapped in it. After briquetting, all of this air is gone away. And what you have here on this side is a piece after briquetting, and now water is added to it. So what you'll see in a second is that when water reaches the straw, then it absorbs the water. So the straw goes from hydrophobic to hydrophilic. Here we have a briquette press in operation. This one is shown in a silo. This is not the normal way if it's with straw. But here you see the material coming down. If it was straw, you know, shortened straw would come down and it would be fed in front of the piston that is moving forth and back. And then a long endless briquette is formed. And this briquette is being transported in the cooling line, in this case to an open container. And then this open container could be taken to one or another biogas plant, or instead of the container here, you could in reality send it to the biogas plant, the reactor directly. What happens now when you have the briquette where you've broken the structure and you put that to water, Here you have a small piece of briquette, 100 gram. Here you have shredded straw. It's not the 2 millimeter or 2.5 millimeter that Lars was speaking about, but it's longer. And then after 10-15 minutes, this briquette has absorbed the moisture. The straw here is still floating, and you have the floating layer that has been one of the major issues for straw in the biogas plants. Then figures, I mean, these figures, I'm sure that a lot of these figures is with the help of Henrik that they are done. Here we have the different types of mesophilic, thermophilic, and what we normally would say thermophilic, that would give you 300 liters of methane per kilo. But as written down here, the gas yield will depend fully on what type of biogas plant it is and how it's been running. Henrik was telling this as well, that they were doing trials at Foulum Aarhus University now. And Torben Bunde, part owner of Kinetic Biofuel, he's working down in this advanced industrial and getting those very high figures that Henrik had in his presentation. Here again, a picture like you saw earlier from Foulum. Here at this solution that was standing at Foulum was with Linka. You see the red color that from Linka hammer mill into the briquette press, and then the cooling line here. The briquettes were normally taken up here on top of the reactor, and then they were screwed or fed down below the surface and then dissolved in the plant. Here I've shown some scientific reports done at Aarhus University. I'm 100% sure that Henrik's name would be on each and every one of those. What is then needed to make briquettes? Quite similar to what Lars was showing. You have a bale conveyor, you have one that takes the bale apart, you have a hammer mill, you have some transportation, by air, and then the difference from his system is that we put the briquette press at the end of the straw preparation line. The straw that is needed here is good quality straw. It's dry straw that's needed. It's not secunda straw or anything like that that should be used. Here we see some pictures from a line in UK. Here you have the straw bales coming up, taken apart. You have the hammer mill here. You have a mixer, and then from the mixer, in this case, into one of two briquette presses. The briquettes will just fall on the floor, and then they'll be taken with vehicles to the feed box here. You see this picture where the briquettes are here in the corner, and here you see cow dung and then fed into the reactor. What are the costs? Lars showed some of his costs. Now I'm this lucky that my figures are slightly lower than his. I say that it's 60 to 100 kilowatt per ton of briquettes manufactured. 60 ton, that's or 60 kilowatt, sorry, 60 kilowatt per ton is for the briquette press. And when you have the briquetting or the straw preparation line, then it's the 100 kilowatt that is needed per ton. Labor, we say it's a quarter of a person to one person per shift. It is a string remover on the line if there is less people is needed. If there is a crane, as Lars mentioned in his, then of course way less. So fully depending on how automized you make the solution. Cost of service and maintenance is an open question, but will depend on quality of straw. We say it's 5 to 7 euro per ton that you produce. That is a cost. Then in Denmark, we have 3 factories where they manufacture briquettes. It was mentioned earlier that about 40% of the gas being consumed in Denmark comes from biogas plants. These biogas plants are the black spots around here. And the idea for these three manufacturers is that they can supply to biogas plants within their driving distance. The companies are Easy Agricare, it's Sønderjysk Halmindustri, and BioBriket. At the last one, BioBriket, we have a solution standing together with equipment from Linka and Euromilling. Then this is the way that it has been intended. You make briquettes, you send it into the reactor, the biogas plant, you make methane, and you can get a CO2 certificate. But as I mentioned a little earlier, some last 2 years with bad harvest or too wet and whatever, straw was less, and straw less and bias enough made the prices go up. So this combined with that Ukraine, Russia, when they started, the energy prices went outrageous high. It's fallen down. So the way it's happening today in Denmark is in reality that you make the briquettes will absorb moisture. The briquettes will be taken for bedding. The bedding will be going to the biogas plants as it's done beforehand, and then you'll get the methane. But what you will get with this and what makes the business much more feasible now is that you get a higher CO2 certificate than if you used it directly. Then advances, second generation raw material, plenty of straw available in most countries. Straw will absorb. Briquettes can give you the higher yield of gas. It's due to the density, it gives you logistical advantage. You can transport it easily. And then concept is patent and proven through test at the University of Aarhus. Then last one, who are we? Kinetic Biofuel, we are a company that has two owners. One owner is CF Nielsen that has manufactured briquette presses the last 60 years. The other one is Biofuel Technology with Torben Bunde. And they are the ones that are in these trials with 100% straw-based biogas plants out in Folum. So this was what I had. So if you have questions, I mean, put them later or contact us later. You're most welcome.
Thank you, Henrik, for a very nice presentation. I can see in the chat that there has been some questions if the slide will be shared afterwards, and I hope that the presenters will allow that. Normally they will, because everybody saw it anyway. So if you all three agree, then we'll send a copy of the presentation as PDF files for the participant at the webinar afterwards. So could you approve that by now? So yes, that was approval all the way around. And then if anybody has more questions, they're very welcome by now. There's a question from Anne who asks, I assume that if you have biogas production based on straw, require that you get a source of water. Is that correct? Henrik, that must be for you.
I mean, we are two Henriks.
Sorry about that. Henrik Møller.
Okay, yeah. Of course, starting up a process needs some liquid. You cannot run on straw alone, but as soon as you are in a balance, you can keep on recycling the water. So you can separate the digestate and take the water to the inlet again. So in general, you can be almost self-supplying with the liquid part, with only minor use of water.
Yes, if I could add a comment to Henrik's last presentation, Christiansen's, that the pricing of the straw in Denmark by now is quite high. and meaning that there has to be share the cost for the straw by using it as bedding first. That means that the pricing for the biogas production part of it is going down and make it feasible again. But as is now, the direct use of good quality straw for biogas production, that's might not be the best business. Any more questions for the three presenters? Can't see more in the.
And
Anna
can
has
I
a-
ask?
Yeah. Can
Sorry.
I do it?
Yes, sure.
Directly. Yes, it's because the water content in the straw will vary each year, depending on the growing season. And when you make briquettes, you have this very high, or you have a very specific demand for the water content. Will this not increase the operation cost if you have a year or two maybe in a row where you have very low quality straw?
I suppose this must be a question for this, Henrik. I mean, we need to have straw normally below 20%. We have clients that is running up to 25% high moisture, but the content of the water in the briquetting process has nothing to do with the process afterwards. The challenge is, of course, if you have a very wet year and no dry straw is harvested, then there's no raw material available for the briquetting. But it's not been that bad. It's more a fighting in the market about who's willing to pay most for the raw material.
And I can see there's another question from Mads. Mads, please.
Yes, the approach Lars from Linke had on energy consumption versus particle length is very interesting. Do you have any thoughts on energy consumption in accessible surface area of the particle? If you open one large particle and make it for a big surface area for bacteria to access.
Lars, do you have an answer for that?
Yeah. Of course, you're making it into smaller particles. It's easier for the bacterial to enter the cellulose because there's a bigger area to enter. But it's also depend of the retention time because then the time is longer for the bacterial to get into the center of the straw.
If I could add a comment as well, then I showed some of these inline choppers that are used, and of course they are used with that specific purpose of cutting the straw further down and making a bigger surface on the straw available for the bacteria. So that can be done by inline cutting as well. And
I think I can also just comment on it. There's no clear trend that it helps a lot to make it extremely small particles. So down to maybe 1-2 millimeter makes sense. Going below that, at least what we have done, is not indicating that you get more out of it.
If I can add a comment to that.
Yes, come on.
We have been doing some tests in our facilities in Nature Energy in Kværs. And actually, we will start running at 2.5 millimeter, and the retention time in Kværs is 35 days. Even if we added up to 8 millimeter, we couldn't see a result at the gas shield. So that means it's not feasible to do it in smaller sizes because of the power consumptions. It was all.
So I also think you might do in some cases because of viscosity. If you want to run on a very high dry matter, it can make sense to make it in very small particles. But from a gas shield perspective, it seems that the gain to go very, very low is we can't see it in lab test at least. So, and even maybe 5 millimeter, 10 millimeter, maybe it doesn't give very much additional to go below that.
Sorry, but the time is running out. There's a last question for you, Henrik. The 2 anaerobic digestion plants in Denmark using large amounts of straw. Could you elaborate on how they are pre-treating the straw?
So both of these plants, they have a type of eye grinder, hay buster eye grinder system where they have a hammer mill taking the size down, and then a silage process on the back end after that. So we did silage in extremely big amounts in very, very big silage.
Okay, it's still dropping questions in, but sorry, we are running out of time. So thank you all for participating, and thank you especially for the presenters to give us your presents. It has been very informative, and I hope that the participant could use this. As I mentioned in the start of the webinar, I'll send out a email with a link for a small survey, and I hope you'll use 2 minutes to answer the question in this small survey. But for now, thank you especially for the presenters, and thank you all for participating, and hope to see you at some of the other events coming up for the ALFA projects. So that's it for now.
Yeah.
Bye.
Bye-bye.
Thank
you. Bye.
Louise, jeg lukker, så kan vi lige tage dem på telefonen bagefter. Har du gemt præsentationen?
Det skulle den gerne automatisk.
Kan du sende mig